Hey there, welcome to a quick little video tutorial on the rate law. So this will outline ways that we study the rates of reactions when we don't have time data available to us. So the goal here is to define the rate law and the general rate law expression. It's a mathematical formula. We'll learn the terms order and total order for one reactant and multi-reactant reactions. We'll understand what order means with respect to graphs and the effects on rates, and then we'll compare experimental data to the rate law to determine certain outcomes. So, the rate law is a mathematical expression that calculates rate as a function of reaction concentration. And in this case, let me switch there, there's no time involved in the measurements for this. So if we had time, we would be able to do our rate calculation, which was the change in concentration over the change in time, or really any measure. It could have been grams, moles, something like that. So we've studied that already when we talk about it, and that's called the integrated rate law. What we're going to learn about here is the differential rate law, which does not rely on time. And how we choose which one to use is dependent on the data that we're given. If we're given time data and changes in measures, we can use the integrated rate law. When we're not, we have to use a little bit more complex of a procedure. So for any chemical reaction, and homogeneous means that everything is in the same state. Okay, so those are the systems that we'll look for. When that's not the case, it complicates it a bit. We've got reactants A and B, and their coefficients in a balanced equation are little a and little b. To determine what the rate is, okay, what we say is that the rate is proportional to the concentrations. So that's called a relationship. What that means is if the concentration increases, the rate increases as well. Right? So that's a proportional relationship, and that's what the little symbol in the middle means. Now, when we change a relationship to a function or an equation, we have to replace that proportionality symbol, alpha, with an equal sign and a constant. Right? And a constant describes the slope that relates the variables concentration and rate in this case. So the rate law, which is this bubbled in here, okay, we'll just give that the name. So that's called the rate law. The first one is just a description, right? It's not useful mathematically other than to identify the pattern, whereas the second one is a mathematical expression where we can determine. Now, the exponents m and n are not the coefficients, okay, which were these here. And we had said that earlier, a and b are coefficients. So it's not the case. And by real numbers, what we should change that to is any whole number, any positive whole number, or positive integer. Okay, so there'll be exponents that we determine experimentally, right, and we call that empirical. Just another term that you might see going forward. So whenever you see empirical data, that means it was actually determined using an experiment. So we can determine the rate of any reaction based on the initial concentration of the reactants. Notice how the products aren't in this. It's dependent on the reactants because that's all that's there at the beginning of a reaction. There are no products. So here's an example. We've got a complex reaction. Let's change that to an arrow. Right, where the rate is given as the rate is equal to K. Remember, that describes the relationship between rate and concentration. The concentration of each reactant, okay, so we've got selenic acid, iodide ions, and hydrogen ions, raised to some exponent. So in this case, the exponents are not the coefficients, right? So it's not 1, 6, and 4, right? But we'll be given some information to determine them. So here we're told that the exponents are 1, 3, and 2. So if we were to rewrite that, the rate is equal to K times the concentration of selenic acid to the exponent of 1 times iodine ions to the exponent of 3 times hydrogen ions to the exponent of 2. So those are given, the exponents, or we'll see next we have enough information to determine what they are. And in this case, we're also told that the rate constant, which is K, has a value of 5 times 10 to the power of 5, which is 500,000 at 0 degrees Celsius. We'll talk about the units on this later. They're a little more complex than normal. So what we're asked is to determine, just an example here, the rate of the reaction given these concentrations. So because we were given all of the numbers, it's very straightforward. We plug this in based on the equation we have at the top, right? The rate times K, which we're told is 5 times 10 to the power of 5, liters 5 per mole 5 times second, times each concentration. So selenic acid, 2 to the negative 2 to the power of 1, iodide, 2 to the 10 to the negative 3, and I'm just leaving the units out for simplicity here. The exponent of 3 times 1.1 times 10 to the negative 3 to the exponent of 2. All right, now carefully punch that in, pause and try it. All right, and be careful with your scientific notation and exponents. Don't forget to add those in. I suggest you use brackets to help you do that. So I'm just going to keep typing things in one by one. We've got these here. Every time we enter a number in scientific notation, we'll put a set of brackets around it to ensure that we're following proper BEDMAS in the calculator. So we've got 2e negative 3. Put that in brackets to the exponent of 3. Right, and I'm just going along here. We've got 1.1 e negative 3 to the exponent of 2 in this case. Okay, and we get a final answer of 9.68 times 10 to the power of negative 11, and the units for rate are moles per liter per second. All right, so we're allowed to determine the rate at these concentrations given that relationship there. Now, that's the correct answer, and you can follow the exponent laws to verify that. And what we'll want to note is that this is the instantaneous rate, right? And why is that? Well, because as a reaction happens, the rate changes. As soon as that reaction happens, those rates decrease. Those concentrations decrease. So as the concentration decreases, the rate decreases as well. Okay, so it's an instantaneous value. It's not dependent on time, and that's why it was the differential rate law. So it's the math involved with calculating the slope of a tangent at one point in time, right? Whereas with our integral rate law, we're looking at a larger timeline, so an average rate. So 2 new terms for us, order of reaction and total order. So the exponent used to describe the relationship is called the order, and that's of a specific reactant. The total order is the sum of all exponents in a rate law. And it doesn't give us as much information, but it's a useful value as well. So looking at our previous example, this was our rate law. Okay. So if we look at the individual exponents and add them up, they add up to 6. So that means this is a 6th order reaction. That's not going to be much use for us other than the units on K. So we'll spend some time with this. The units on K are as follows. So the units for K are always liters over mole per second. And there's an exponent of n minus 1 on liters and moles. The n represents the total order of the reaction. So the higher that is, the higher the variable is on K in the exponents. So that's the purpose of the total order, really, for our concern at this point. The other exponents, so the individual exponents, represent specific orders. So first order, an exponent of 1, in this case represents the relationship between the rate of selenic acid and the rate of the reaction. We're going to look at each of these independently, what the numbers actually mean, because they describe how the rate changes, right? How R changes with changes to the concentration of that specific reactant. All right, so it's an individual identifier. Okay. So make a note of this. The units on K always depend on the overall order, the total order, and it will always be liters over mole second, right? And the exponent on liters and moles will be one less than the total order. So what does it mean? Well, let's start with 0. We'll look at 0, 1, 2, and we'll mention 3. So if an exponent is 0, it means the rate does not change if the concentration of the reactant changes. It's constant. So these reactants don't get included in the rate law because anything with an exponent of 0 is just 1, and they will be canceled out. They're not 0. A to the exponent 0 is not 0, or else the whole function would be 0. It just means that the rate is independent of the reactant concentrations. First order reactions. Whatever factor the reactant changes by, the rate changes by as well. And that's when you see an exponent of 1. So for example, if we double the concentration of a reactant, the rate will also double. Okay, so that's very straightforward. If we were to graph that, we have the rate, we have the change in concentration. We'll just use A here. This will be a linear relationship. Okay, it'll get a predictable outcome each time. So that's what first order means whenever you see that first exponent. Second order reaction means whatever factor the reactant changes by, the rate changes by that factor squared. So here's our example. If the concentration is doubled, and double means times 2, so we're always looking at multiplication for this. The rate will be increased by a factor of 4 because it's the rate, the factor the concentration changes by, squared for a second order reaction, which means the rate will change by a factor of 4, right? And that will describe when there's an exponent of 2. So if we continue this pattern, again, it's describing how the rate changes with changes in concentration. If it's third order, it's the factor cubed. So in general, what we can say, the factor that the concentration changes by to the exponent, which represents the order, is equal to the factor that the rate changes by. Right? So this applies to any rate. If it's an 8th order reaction and then we double concentration, it would be 2 to the exponent of 8 is what the 2 to the exponent of 8 is what the rate will change by. Okay, so make a note of this because we'll use this to interpret experimental data now. So we're going to skip this. You can read this as general info if you'd like. We will skip this as well. Again, this just describes experimental data readouts and how you would determine what order a reaction is based on data that you have from a graph. Okay, so there's a couple of different functions that are there. So how do we determine what the exponents are using experimental data? Well, what we're going to look at is what the rate changes by as the concentration changes of the reactants. So how we're going to do this, and these are your steps to follow given experimental data. We'll look at the change of one reactant's concentration, and we'll keep all of the other concentrations constant. We do that to have control variables. We just want to see what one effect has on the rate. Okay, so let's look at the example here with the data on the next slide. So given this reaction, we're going to determine what the rate law is with the exponents k and the units on k. So looking at the reaction, nitrogen dioxide and fluorine, we've got 2 nitrogen dioxide plus fluorine, and just to make sure we get this right, 2NO2F. So if that's our reaction here, right, the rate law is based on the reactants. So what we can say right off the bat is R is equal to K times NO2 to the exponent of M times fluorine to some exponent N. Again, in this case, the exponents are not equal to the coefficients. So now we've got all this experimental data. Trial just means the number of times that the reaction was conducted. And you can see that the concentrations changed each time for those. Beside that, you have the rate of the reaction. So that'll describe how fast the reaction proceeded. So if you look at the trial data, the concentrations, right, when we increased one of them, the rate got faster. Okay. So here's what we're going to do. We're going to use this data here to determine what the exponents are. So let's start with the exponent of m. So for exponent m, what we want to look at is two trials where the concentration of NO2 changes, okay, because that's what m is describing. We're trying to figure out how the concentrations change affects the rate itself. So if we look at the chart here, the concentration of NO2 changes in trials 1 and 2, and F2 fluorine stays the same. That's important. It can't change because if both change, like it does in trials 1 and 3, we don't know which one had the effect on the rate itself. Okay? So we look for trials where the reactant attached to the exponent changes and the others stay the same. So in this case, the concentration was doubled. And what happened to the rate? It was also doubled. So these are the factors that the reactions change by. So for M, we say use trials 1 and 2 because NO2 stays the same, and that's where the M is part of. Right? And if you remember that formula we talked about, the factor that the concentration changed by to the power is equal to the factor that the rate changes by. So in this case, the concentration was doubled. Right? We're trying to find the exponent, and when it was doubled, the rate was doubled. Right? So an equal change in both means that it's a first order reaction. So the exponent is 1. So now we'll do the same thing for N. And we're going to look, because N is on fluorine, we're going to look for trials where fluorine changes and nitrogen dioxide stays the same. So what trials is that? We can take a second while we write this down. In trials 2 and 3, okay, fluorine changes, but nitrogen dioxide stays the same at 0.2 each. So we'll just look here. To make it easy, we'll go for multiplication. Between trials 3 and 2, the concentration was doubled. And when the concentration was doubled, the rate was doubled. Now you can look at it as halved as well, and you'll get the same thing. It's just a little bit more difficult to work with fractions and exponents. But if you're comfortable with it, not an issue. So again, the concentration doubled. We're trying to find the exponent that really makes that relationship, and the rate doubled. So n is equal to 1 as well. Right? Now, using this data, we found what our exponents are. So we can say R is equal to K times NO2 to the power of 1 times F2 to the power of 1. Right? So this is our general rate law now. So what does that mean? It means it's overall second order reaction because we added the exponents, right? And it's first order for each reactant. So that means whatever we change those by, the rate will. And if we double both, then the rate doubles 2 times, it actually quadruples. So we multiply the effects of each of those. Now to find K, right, all we do is choose a trial and plug in the data. Okay, and it can say any trial, not trial 1. Choose one of the trials and sub in the data to find out the value of K. And remember that the units are liter and -1 over mole and -1 times second in this case, right? Where N is equal to the overall order. So in this case, it would be a second overall order, so they each have the exponent of 1 on them. So you can try that and punch it in, right? Again, be careful with your scientific notation. Okay, so that goes over how we determine the exponents given experimental data and the rate law. Again, there's no information about time, so we use this method, the general rate law. And if we did have time data, we'd use the integral rate law, which describes the change in concentration over change in time. So hopefully that clears up the process for reading the data. There's some homework questions and chapter review. Good luck with the practice, and thank you for watching again.